All right, let's talk about one of the absolute biggest headaches in computer science. I'm talking about managing pure, unadulterated chaos.
So picture this. You've got a system, right? And there are a million things happening all at once. How on earth do you get them all to play nicely together instead of just, well, crashing and burning? And this isn't some far-off theoretical puzzle. This is the reality of pretty much all modern computing. This whole mess, yeah, that's what we call concurrency. Is when you have tons of different processes all running in these overlapping time periods. Honestly, trying to manage it can feel like you're a conductor, but your orchestra is just a bunch of musicians, and every single one of them is playing a completely different song. Total chaos.
But what if there was a way to fix that? You know, a master plan to bring some harmony to all that noise. Well, there is. And for that, we need to dive into the work of a true giant in computer science, C.A.R. Hoare, and his absolutely brilliant solution. He called it Communicating Sequential Processes, or CSP for short. And you know that name tells you everything. Here's Hoare's big idea. To manage all this complexity, you shouldn't get bogged down in what's happening inside each process. No, you should focus on how they talk to each other. The real magic, the secret sauce, is all in the interaction.
And that right there, that's the core philosophy. You just shift your focus away from the messy, complicated guts of each process and instead look at the clean, simple logic of how they interact. When you do that, suddenly you have this incredibly powerful new way to think about the entire system. It's just a brilliant simplification, and it's what makes all that chaos, well, manageable.
So, how does CSP actually pull this off? Well, it all comes down to two really powerful but surprisingly simple-sounding principles. Let's break them down.
Okay. First up, we have principle number 1, compositionality. Now, this isn't just a software thing. It's a core idea in all of engineering, and CSP just applies it to code in this really masterful way.
The best way to think about it is like building with Lego bricks. Seriously, you start with these simple individual bricks. Those are your basic processes. You know exactly what each little brick does, right? Then you use these really clear, defined rules to snap them together. And by doing that, by combining these simple, predictable parts, you can build these unbelievably complex and rock-solid systems. And the best part? You can actually understand the whole thing just by understanding its simple little parts.
All right, on to principle number 2. And this is where CSP really starts to look different from a lot of other models out there. It's called synchronous communication. And this idea, it demands absolute perfect timing. For any communication to happen, both the process sending the message and the one receiving it have to be ready at the exact same moment. It's just like a baton pass in a relay race. It has to be perfectly timed. If one runner is a little early or a little late, the whole thing fails. You can't just drop the baton on the track and hope the next runner finds it. It's all or nothing, right then and there.
Now, this synchronous way of doing things is a million miles away from how most of our systems work today. Just think about sending an email. That's asynchronous, right? You type it, you hit send, it goes into a mailbox somewhere, and you just move on with your day, assuming it'll get picked up eventually. CSP is the total opposite of that. It's a guaranteed, instantaneous handshake. And that one simple rule, it wipes out a huge amount of uncertainty from the entire system.
Okay, so this is where we get to the real magic of CSP, because it's not just a bunch of clever ideas. No, it's a whole system built on the rock-solid foundation of mathematical certainty. And that is what lets us build an incredible amount of trust right into our software from the ground up.
See, CSP is what's known as a process algebra. I know, that sounds super intimidating. But all it really means is that it's a formal language that has its own set of rules. It's kind of like the algebra you learned back in school. But this one is designed specifically to describe how systems interact with each other.
It is literally the mathematics of interaction, and having a formal language like this means we can finally move beyond just testing our code and hoping for the best. We can actually reason about how these concurrent systems are going to behave. And, this is the big one, we can mathematically prove, that a system is free from certain types of catastrophic errors.
So, what does this actually look like in practice? It's basically a 3-step process. First, you describe your system using CSP's formal language. Second, you apply these super rigorous mathematical rules to define exactly how it's supposed to behave. And then third, you can unleash automated tools, software like the FDR3 refinement checker, to just go through your model and mechanically verify that your design is solid, that it's free of nasty problems like deadlock. And all of this leads to this incredibly powerful idea called correctness by construction. Think about that. Instead of building something and then spending weeks trying to hunt down all the bugs, you're building a system that is provably correct from the very first line of its design. It's a total game changer.
So this whole thing kicked off with a single paper back in 1978. But where did it go from there? What happened next? Well, CSP didn't just stay locked up in some ivory tower. Oh no, it went on to have a huge impact on the real world.
Hoare's paper wasn't one of those things that just collected dust on a shelf. The ideas practically leaped off the page from theory into practice. By the 1980s, they were the inspiration for a whole programming language called Occam, which was built to power this amazing piece of hardware, the Inmost transputer, a chip designed from the ground up for parallel computing. And you can draw a direct line from that, all the way to today, where CSP's core principles are alive and well in the verification tools that help make our modern complex systems reliable.
And the impact isn't just theoretical. It's concrete and it's far-reaching. We're talking about the Occam language, the transputer hardware, but also crucial algorithms that prevent those dreaded system-wide freezes we call deadlocks. And looking even bigger, its principles became the foundation for huge ideas like Hoare logic and the Verified Software Initiative. They're all part of this grand quest, this search for software that is provably correct and fundamentally trustworthy.
You know, this all comes back to Hoare's central belief, his whole philosophy. He saw programming as more than just a craft. To him, it was a formal mathematical discipline. In his view, programs aren't just a list of instructions for a dumb machine. They are mathematical expressions that you can, and should, reason about with the full power and rigor of logic.
And that leaves us with a pretty fascinating question, especially for today. In this whole move fast and break things world, in our rush to build and iterate as quickly as possible, have we maybe lost touch with the power and, frankly, the elegance of these formal methods? Is there a hidden price we're paying for all that speed? And maybe, just maybe, is the art of proving a program correct before you even run it something we desperately need to rediscover?